Hello and welcome to the next episode of Yule programming course. In this episode, we will be a bit more practical. We will look into how Yule works in practice. We will see that in Remix. And without any further ado, let's go. As you already know, you declare Yule inside assembly block. The problem is that Yule is not really assembly language. It's a level above assembly language, but for whatever reason, creators of the language just decided that it's like this. Let's start with the simplest possible thing, which is declaring variables. This is a bit different to Solidity because in Solidity you have, for example, you declare uint name of the variable, test variable, assign it value or not, let's say that it's 15, and this is it. However, in case of assembly, you are using this let block. And we have, let's say, our test variable assembly. And another difference, let's make it 16. You can see here there are a few differences between Solidity and Yule. First of all, you are using let to define a variable. Assign operator is not equal strictly, but it's colon equals. You have to add this colon. Without this colon, it will just throw an error on you that literal identifier expected. This is because there is like missing colon. Why is that? Don't ask me. And the last thing, you don't use semicolons in Yule. And what about types? Because here we had u in 256. If we want to define like integer with 64 bits, that 64 is 13. Okay, all good. How to do that in assembly? Well, you can't. There is only one type. This is one word. So documentation of Solidity strictly says that there is only one type defining the word. In case of EDM, dialect of Yule, this is only u in 256 because this is a single word of EVM. This is not implemented yet. However, in the future, it might be possible that Yule will introduce data types. According to the documentation, as you can see here, it's possible to define, like it's not possible right now, but it might be possible in the future that you may define type of the value, like here, for example, u in 256 and u in 32. But again, this is not implemented as of time of recording this video. So next, you cannot really use other types than a single word. In our case, u in 256. However, you can use them if they are defined outside. So for example, we have test 64 here. We can, for example, say that test 64 now has value of 9. And this is completely fine. You can use that and like the language will accept that. And we can even see if it really works by returning it. Sorry, it's returns and 64. Okay. So let's deploy it and see for ourselves. Yes, this is 9, just as expected. You can even define some return variables and assign them values. So you can use any variables outside in the same scope as you would do in Solidity. So our rest red variable, let's make it 333. Okay, yeah. It still returns this value because we explicitly return it, but we don't have to if we put name here. So it will work still. And you can see that it does not return any problems with that. Let's see if this is the value that we set. Yes, 333, just as we said here. And actually, let's create a second test when I will show you that you can, in the same manner, use the parameters sent to the function. So now we have additional function add, which hopefully, given two numbers, will return a result of addition of both. Yep, just as expected, we pass 5 and 4 and the int results 9. So you saw here that first of all, we can use parameters outside, even call data parameters. We can use the result parameter as well, and we can do actions in between. In this case, we used add function. So as I already told before, the YUL function names are named after EVM opcodes. So if you have any opcode that you know, probably, most probably, the name of it will be the same in case of YUL. The difference is that, as I said before, YUL is expression language. So most, like not all, but most of the operations return some value, and you can use that. And for example, what if we wanted another function, add +1, and we wanted to add additional 1 to the result of addition? So we would do that something like this: result equals okay, and hopefully this function will, given the same parameters, will return us 10. So let's give 5 and 4. Okay, gives 10 as expected. But this kind of writing the expression is a kind of verbose. The question is, can we do better? Yes, we can. We can do it more efficiently. We can chain operations together. So, for example, instead of writing this in 2 lines, we can shorten it and write it all in 1 line. So we can write add 1 to it. And let's see if this is the same. 5, 4, result is 10. Okay, works as expected. Why is that? Because almost each operation returns result from the operation that you can reuse in other operations. So we can do actually the same in Solidity, for example. You can use some function as a parameter of the function result as a parameter, and you don't have to declare the special variable. You can directly set the function invocation inside of the parameter, and it will first invoke this function and put the result to the parameter. This is the same in YUL. And actually, how do you read that? You can read it from right to left, because YUL evaluates expressions from right to left. So the opcodes that would be here, it would be, remember that YUL does not allow you to modify stack, so it will be pushed for you. So we have this push 32 because we are having the whole uint, so it will push 32 bytes of A, will be push 32B, then it will call add on them, then it will push 1 to the stack, and it will call add on them. So actually, the returning value you can think about as you directly use the stack, because add operation takes 2 parameters and returns 1 to the stack. So the 1 parameter that is being returned, you can actually reuse it in another operation. So this is super useful compared to raw EVM opcodes. Okay, so now let's say that we want to introduce the divide operation. This is very similar to add. The opcode just differs. And okay, let's see if it works. We are passing like 6 divided by 2. It's free, completely fine. But what if I do something unexpected? Divided by 0. The call succeeds. I get return 0. However, you can remember that solidity reverts in those cases. So what if you want to have the same behavior in YUL? Well, we have to do the check ourselves. So let's make this one. So first, let's see if it really works, and then I will tell you what changes I made. Any number divided by 0 should revert. Yes, transaction has been reverted. 4 divided by 2 give me return 2. So it works. So what I did here is I used if. So in YUL, of course, you may have conditionals, and conditionals are way simpler than in Solidity. You only have if, you don't have else if. Let's say it's 0a, it will not really work. You can see else if just doesn't really work. What if we try to have else? No, it also doesn't work. So we only have ifs. Well, this is not a problem. Like else if and else is just a syntactic sugar to help you out with development, and just not there in YUL, but it really is not the end of the world, actually. So what I did here is introduce the if statement. And one of the opcodes is E0, which just if this is true, it returns 1. And actually we are using the result of this E0 return. And if this is true, that means that B is 0, we are reverting. And in revert, remember, we are passing the memory offset that we want to start to give the revert message and the length of it. In this particular case, I don't really care about reverting with any specific value, but I could actually store the message inside of the memory and then pass it start of the message and its length to revert with the specific reason. So actually, I can either use this directly, or I can use any other variable that I declare, and it works just the same way. So actually, I can even do things like pass any other number like B, and it also will work in this particular case. So if will be effective if the variable here, like if the value here, no matter if this is value returned after evaluation of other opcodes, or this is like value as here as value B, it will be effective if this is non-zero. So in our case, if we pass any B that is bigger than 0, 1, 10, million, like gazillion, any number that is not 0 will actually make this branch effective. And only 0 is considered false, and anything other is considered true. We can see, okay, it reverted because B is true, is 1, but actually if we pass any other number, it will be the same. It will actually only work if this is 0. But yeah, this is just to show you how the if really works. And actually, let's build on these previous examples and build a simple calculator in YUL. So we'll need an enum for that. And we have like 4 operations: add, subtract, multiply, and divide. So we have our function calculator, which additionally takes our operation. A bit of break. I have to check the... Okay, let's make it really simple. First, we are having our switch statement. Switch OP. And now, if this is case 0, case 0, because if you don't know, in Solidity, enums are just simple numbers and they start with 0, 2, and 3. Okay. So case 0, this is our add. So in this case, our result is add A and B. So I written a very simple calculator. It takes A, B, and enum of operation, and we have our switch. In case this is 0, which is our first operation, it result is a result of addition of two numbers. In case this is 1, this is subtract. Then we have multiplication and division. And default, in case that nothing is matched, I want to revert it. So let's quickly see if it really works. We have our calc. Let's see, we have our number 4 and number B is 2. If we pass operation 0, result is 6, which is cool because 4 plus 2 is 6. 4 minus 2 is 2. So it looks like it works. And now what if we pass any enum value that is not here? It reverts, but you have to know here that Solidity introduces some safeguards that you don't see that are there for you. So in case of enums, it checks if the value is not bigger than the last element here. If you were to write it yourself, there would not be such a safeguards. So this is something that you have to remember if you are writing pure UL, for example, or pure opcodes. And finally, we have our loops. In case of UL, there is like only one loop. This is for loop, and there is no like while, do while, or things like that. Oh, but before jumping into for loop, one additional thing I want to add about switch statement. In case of UL, if any case is being matched, all the other cases are not being executed, because in some languages you have to use the break statement after each. This keyword in UL is only reserved for really loops. You can break out of loops or continue loops. In case of switch, this is invalid opcode, and you have to remember that if in any case is being matched, no other case will be matched. This is not the case in many other languages, so I want to say to you. Okay, and now we will create lousy multiplication, and this is very lousy because I just want to show you how for loops work inside of UL. The syntax is a bit exotic, I would say, and we will implement multiplication by constant additions. You should never do that. Okay. Just a moment. We are not recording that yet. Okay, so I did like really lousy multiply for you. One thing I want to add here, it won't work really. It won't work if you want to multiply 1 by anything. It will just add it, and normally if you multiply anything by 1, it returns you 1. But I really wanted just to show you how the for loop works. So let's imagine that this is perfectly fine, but without the multiplication function, just for now, just for the sake of argument. So we have a for loop And this is very similar to any for loop that you know, to for loop, for example, from Solidity, but the parts of the parameters you pass to for loop are written in different syntax, because in Solidity you have like 3 parts. First, you are declaring your counter, then you have semicolon, and then you declare the condition that will end the loop, and then you have semicolon, and then you have to tell what happens each time the loop is being run. So the same is being done in Yule. It just like the syntax is a bit different. So first part, our declaring of variables is in square brackets, and you can declare multiple variables here. And of course, we have the our terminating condition. In this case, if our counter I is lower than B, we have to stop. And then what happens at every run of the loop, we are adding 1 to our counter. And inside of this loop, what we are doing, we are just adding A to our accumulator X that we defined before. And at the end, when the for loop finishes, we are assigning X to our result. And that's it. So this is all concerning Yule basics. I hope you learned something new. If you have some questions, feel free to add them to comments below the video, and I will surely try to respond to each of them. This is all for now, and see you in the next one.